Now let us come to the discharge of a fluid, a Newtonian fluid. So when I say Newtonian fluid means it obeys Newton's law of viscosity. So Poiseuilles law for the discharge of liquid through a circular horizontal tube. So we are concerned about that how much fluid will flow through a pipe of uniform cross section, that is the circular cross section placed horizontally across which there is a pressure difference. So we have a liquid here, we have a flow of liquid through a pipe. This is the horizontal pipe with uniform cross section. So you see this cross section is circular and the liquid flows through it, and you see across the two ends I have taken this length as L, and here we have a pressure, excess pressure of P. That means the pressure difference, there must be a pressure difference so as the liquid will flow. So we have maintained a pressure difference of P here. So consider a flow of Newtonian fluid of density rho through a circular horizontal tube of length L and radius R. Let the coefficient of viscosity of the fluid be eta. The fluid flows such that a pressure difference of P is applied across the two cross sections. So we have to continuously apply pressure difference between here, because this is a Newtonian fluid and there is a viscous drag to it. So first of all I have to calculate what is the velocity profile, because I know that the velocity very close to the cylindrical walls has a zero velocity and at the center we have a large velocity. So what we do, we just consider a cylinder of radius r, small r. So this is a radius of small r, and you see here, suppose this layer has a velocity v as a, so this velocity v as a function of r is here. So you see this velocity profile is something like this, and as you go on you have a lesser velocities like this. So I don't know, but that what is the profile presently. So it, as you go on it will be decreasing. So according to Newton's, so what we do, let us apply. So now consider an element, consider a cylinder of radius small r inside this as shown in figure. Now consider the equilibrium of the liquid inside this cylinder, inside the cylinder. So this liquid flows with a uniform velocity, so there is no acceleration in the system. So the total drag force, this direction there is a drag force acting, here there is a viscous drag force. So the viscous drag force is equal to the pressure difference at the two sections. So, the total viscous drag force is equal to the force due to hydrostatic pressure difference across the cross sections. So, you see here the force here, F viscous force will be minus eta area. So, the curved surface area is 2 pi r L and the velocity profile is dV by dr. As you go away, the velocity profile normal to the flow is dV by dr. So, very important, normal to the flow. Now, this is equal to the excess pressure. Now, you see excess pressure applied is P and this area is P into pi r square. So, P is not the pressure here, there is a excess pressure. So, you see this force is here, P1 area, P2 area. The difference of this is the excess pressure P into pi r square, the cross sectional area of this part. So, now you see this 1r cancels. I want to know what is V. So, we have 2, this pi also gets cancelled. So, 2 eta L dV is equal to P r square dr. So, if I integrate this whole term, there is one negative here also. So, r is actually 0 at the value of capital R. So, when it is very near to this surface, then this fluid layer has a velocity 0. With the wall, the fluid is at rest, and when it is at R, this velocity is V. So, on integration we get minus 2 eta L V minus 0 is equal to P by 2 R square minus R square. So, this minus can be brought this side. So, we will have V as a function of R. This is P capital R square minus small r square by this is 4 eta L. So, this is the velocity profile. When r is equal to 0, the velocity is P r square by 4 eta L, which is the maximum. Now, let us draw this velocity profile. So, now the velocity profile is this. Let us draw this velocity profile. You see, this is the excess pressure 4 by 4 eta L and this is the quadratic function. So, this is a parabolic path, a parabolic curve. You can see this is our wall and the velocity is at r is equal to r, the velocity becomes 0 and it is maximum here, and this varies as a parabolic curve, which we have seen this curve in the introduction of our viscosity. So, this is the velocity profile. This velocity profile is measured from this center line, and so this curve is here V as a function of r. This r is measured from here. So, this V as a function of r is P by 4 eta L. This is capital R square minus R square. So, here and here both the symmetric, the profile will be symmetric. So, thus the velocity profile is a parabolic curve for a horizontal tube of circular cross section. So, now once I know this velocity profile, then I can calculate the total discharge. So, since the velocity at different layers is different. So, we have to find the discharge in a cylindrical region and then we have to completely integrate it. So, you see this outer one I am just drawing. So, this is the outer one. So, this is of radius r. So, in order to calculate the total discharge, we have taken a differential shell. So, you see here, this is a radius r and the width is dr. So, now consider the discharge of the fluid through a differential cross section of radial width dr at a radius of r. So, this area, so we will have the discharge dq is equal to velocity into the area. So, the area of this shaded cross section is 2 pi r into, this is the circumference, into dr. So, this is the discharge only through this portion. So, this V we will substitute from the velocity profile expression 4 pi eta L, this is r square minus r square 2 pi r dr. So, here dq is equal to p, this p pi, and here it is 2 eta L, we have r square r minus r cube, and this is dr. So, now let us integrate it with the limits r varies from 0 to r. This is the total discharge p pi 2 eta L, then r square, this again r square by 2 minus r to the power 4 by 4, that is p pi by 2 eta L. Now, we put r, so this is r 4 by 2 minus this is r 4 by 4, that is again r to the power 4 by 4. So, this is p pi r to the power 4 by, this is 4 to 8 eta L. So, thus you see that discharge of a fluid through a circular tube is given by, this discharge is p pi r to the power 4 by eta pi L. So, discharge is proportional to p r to the power 4 and inversely proportional to L. So, this is the Poiseuilles law for the discharge of fluid through a circular horizontal tube.